like geoscience and all that, but also give you like an introductory talk about machine learning and why I think it's so interesting. So thanks for coming, and I hope this is going to be interesting for you. I know a lot of people here are really busy, so if you take anything away from this, I think the most important thing is to become a T-shaped person. And if you want to know what that is, I mean, I write about it, other people have talked about it, and I'm going to tell you. But for that, you have to stay. Become knowledgeable in a lot of topics, but an expert in some. So we'll get into that a little bit more and build a portfolio. So really, yeah, build a portfolio of projects, of things you've done, papers you've written, like, yeah, really make yourself stand out a little bit. So keep reading, keep doing classes, they help, and yeah, share what you can. What we're doing today, like, I want to talk about my background a little bit, why you should or shouldn't listen to me, because I'm just another person on the internet with way too many opinions. And there are a lot of reasons why you shouldn't listen to me. But yeah, if you find anything of this relatable, this is just me basically sharing my experience, how I went from geoscience into, yeah, becoming a machine learning engineer now, working in tech, and having a lot of interesting projects to work on. Happy to talk about them in the Q&A later, but I won't get into them right now. And yeah, I want to talk about what machine learning is, what's important in machine learning, and how does geo really apply, or well, how does machine learning apply to geoscience? My path, like you said, I studied in Hamburg in 2011. I have a BSc, I have an MSc. I tried to work on my PhD, but I'm still trying to finish that, which, I mean, this year, it's not easy to finish anything in this year, and a PhD is not easy either. And yeah, it's a strongly linearized path. And my PhD is only in geophysics-ish. There's a lot of machine learning that I've done during my PhD. And now I'm a machine learning engineer. I started this month, and it's really fun. I recommend it to anyone who likes to play with GPUs and is interested in the space. I'm guessing this is the interesting bit. Why did I change from geoscience? Because like, I like rocks. I still like volcanoes. I'm still find earthquakes fascinating, and like during my PhD, I spent time in Svalbard, and it was fascinating to look at all the different rocks. Like, why would I switch? Well, this is the oil price. This is where I got my BSc. This is where I got my MSc. And I don't think we have to talk about 2020. It's not a great year. I'm not sure if a lot of companies are hiring, and the few that are hiring are strongly invested in tech right now. Yeah, like I really managed to graduate into every recession there was. And since I work in seismics, it's very oil based. So the oil price, like even if I want a job in university, that usually means that a lot of people are going back to university because they got laid off in a company. And I feel like a lot of you might be experiencing something similar right now, and which is also why a lot of people are here right now. So I don't really need that in my life. And there's also climate change. Like, I felt kind of bad with oil and gas. Like, you can debate about that all you want. My personal decision was I wanted to not further the profits of oil companies. That's kind of it. So what is machine learning, and why should you care? If you like, I would love you to like rate what kind of experience you have. You can go to slido.com, put in that code, and you should be able to rate on a scale. how much experience you have, and I'll give you a little bit to answer this. I know we're not that many today, so if this interactive element doesn't work, we'll just skip it. I can see if there's answers coming in, but yeah. Hey, okay, we have one answer. That's a start. That's not too bad. That looks like we have, well, people basically have heard of machine learning, I'm guessing, but don't really have deep experience in it. More on the geoscience side of this. Some very beginners. I hope I can capture this. I kept it relatively open how we're going to talk about this, and to make you really understand why I like machine learning so much. Cool. Thanks for participating. I love this stuff. I love it when people are taking part in in polls, and like, I really miss the feedback of talks. So this is really nice. Thanks for being here. This is old machine learning. Essentially, in the 90s, we had expert systems. So basically, researchers said they're smart and they have some kind of idea how the world works. So they make rule-based systems. And these expert systems, they were really, really hyped in the 90s and, well, 80s, 90s, a little bit in the 2000s. And essentially, it was just a bunch of if-else statements. So if X is over 5, do this. If X is lower than 5, do the other thing, stuff like that. So they work better than not having any decisions. But like, they very quickly got to the limitations. Like, one of my favorite papers, because it's like so interesting to see what they did back in the day, was a paper where they tried to identify humans in pictures. And they did that by matching shapes, so cylinders and blocks, to humans to be able to say where they are. And they, yeah, I don't know, the paper looks really funny, because essentially it's little robots with a ball as a head and a block in the middle, and then 2 cylinders here, and like it's very nice to read. I didn't want to put it in here because, like, I don't know what the rights of that are or how you're handling this, but yeah, it's really interesting to see. But it also explains why we basically had something that's called an AI winter. After a lot of hype around these expert systems, people were really disenchanted with artificial intelligence back then, and yeah, kind of didn't want to invest in it anymore. But how do we do it today? What has changed? So essentially now our computers are learning based on data. So you feed it some data and you feed it some results, and the computers try to figure out for you what the rules are. So you're not coming up with the rules. The computer is learning the rules based on some definitions that you make. So there are actually decision trees that are essentially this: if X is bigger than 5, but there's a lot more if statements in there, and they're figured out automatically based on the data. And the more data you feed it, kind of, there's exceptions to this, but usually the more data you feed it, the better your systems get. So what we're doing here is fitting black box models. And you may have heard it. People really like to, like, especially in geoscience, there's a lot of people that don't like machine learning and that talk about these black box models as if it's a bad thing. But in reality, it's just a statistical term for models that don't have external information in it. You can actually have gray box models as well that have, for example, some physics information in it. So if you have the wave equation in a neural network, for example, that means you have a gray box model, something like that. Why are they so interesting? Some really early work, like 2017, that I made with Lucas Mosser. Definitely look him up. Super smart guy. Steve Purves as well. Like super smart people. Just go to hackathons. I love hackathons. I met a lot of my favorite people at hackathons. But yeah, seismic data and the inversion. And this was done by a black box model, a model that has no physical information. And you can see right here that even though this fault is portrayed pretty well in here, all the layers are pretty well, and it's a naive model. Like there's much better out there now, and you can then go on and include these black box models in physical systems. So you can make them much smarter by including some physical information in neural networks. But like this stuff, it's okay. Like this is seismic data, this is inversion. Do we really know what's going on in the subsurface? Usually we don't. It's really hard. But the stuff that is really interesting on machine learning and that I kind of dream about and that I get really excited about is, well, not seismic data, also because I've been looking at it for 3 years. I'm really happy to look at something else right now. It's self-driving cars, for example, like computers that take an image. I don't know, I have a pointer here, I think, that take an image like this and just tell you, oh, these are cars, this is like a tram, these are people, and just figures that out. And well, here you can see that it's apparently a rich car. But yeah, stuff like that, playing games, figuring stuff out, and just really like, who would have thought 10 years ago that we'd have self-driving cars in 2020 and cannot go anywhere with them because everyone's stuck inside. But well, like it's so fascinating where we've come. Like when I grew up, these chess computers were like Deep Blue were super advanced with experts figuring out how they adjust the rules. And today we have a computer that beats the best people at Go. A problem where the problem space is so much more complicated that before it was just like, even if there were people smart enough to figure out the rules, we wouldn't have enough computing power to calculate the rules. Like it's so fascinating how far we've come with this change to a database learning process, essentially. And you may be wondering, but what is this process? Like, I'm talking about this thing, machine learning. What is the machine? And one of the main things, main machines that we're talking about in modern machine learning, in the thing that powers anything that is called AI, like, I don't really like artificial intelligence, but it's a term people use, is deep learning, which is based on neural networks. And they're really hyped. But neural networks were invented in the 1950s. They are really old. And they've been around in geoscience as well. People have been trying them out all the time. Like the inversion I showed you there, the first inversion, oh, well, the first inversion I know about is from 1995. Like some of you probably weren't even born then. So it's like this stuff is really old and people were always really interested in it. And yeah, this time it's getting so much better. And the main reason behind that is because we have a lot of stronger computers, but also our early neural networks look like this. Let me get out the pointer. So we have our inputs here. We have some kind of connection here. And this is one value. So in your entire seismic, if you take the 2D image that I showed you before, every sample in that seismic would have had to be one input here. So this gets really complicated really quickly. But yeah, then we have connections into these nodes. Usually what happens here, and this is where we get mathy, I won't get too much into it, but essentially you have your input that is multiplied, just simple multiplication with a value, and this value is learned. This value gets adjusted during the machine learning process, and then we have a sum here. So this is just the value, and right here we're summing up these two values. So it's really relatively straightforward to understand, I think. And then everything gets added out to an output. In this case, what you could have is basically two inputs and have a binary outcome, like a yes, no, something like that. Yeah, really, really straightforward in the end. And usually what we do here, we change the value a little bit by applying something we call an activation function. And oftentimes that's like a sigmoid function or like some mathematical function to make our response right here nonlinear. So it can literally be anything that is not a straight line. Quadratic, try it, might work. But this is classic deep learning, and this is this is classic machine learning, and this is deep learning. I didn't put too much work in these figures because I just copied them together real quick, but essentially you have a second layer, and this is already deep learning. That's the magic. But the point is, when you get to these two layers, neural networks become something called a general function approximator. And that means whatever function you can come up with, like x plus 2/5 x squared, x cubed, x to the fourth power, anything like that can be approximated by this type of neural network. So already with two layers, you're Gucci, you can do basically anything. But then we're getting to the really interesting stuff, because building a computer vision system, like something that drives our self-driving cars, is going to be really hard with this. And it's going to become really expensive, because this is one number. So this is already storing 2, 4, 6, around 20 numbers for this small thing. So people had to become really inventive or creative with it, what to do, how to really, how to build better neural networks. And the modern neural networks are not necessarily this kind of thing, although people love to show it. Modern neural networks, sorry about that. Let's get back to that in a second. Modern neural networks look like this. They basically have this receptive field right here. So just like a little square that gets convolved with the input image. And this little square is initialized as a random value. So there is noise in there. Yeah, it's noise. And these values in that square that gets convolved with the image get adjusted. And the learning process in there is really just putting in data, seeing what gets out right here, and then adjusting all the weights in here, like all the little squares get adjusted by stochastic gradient descent. If you've ever taken any class on numeric optimization in geophysics or something like that, it's literally just finding the minimum of your error. So calculating your error here and then walking the path where your error gets the least. And what happens from there is essentially that if you have faces, for example, your low-level features, so the ones in the very first layer here, are just like straight lines a lot of times. And the next layers are then combinations of those lines. So when you have a face data set, a lot of times you have like noses. I think this is an eye right here, another nose, maybe some flat spaces. If you don't have grayscale images right here, you can often see like color separation filters. And then when you get to the deep layers right here, you can start to see basically eigenfaces. So like very standard faces that just get combined out of these filters. And in the end, you have one of those cliche neural networks that just combine to another and then output like 3 classes or something like that. And this is how neural networks really work. It's quite simple. And that's also one of my favorite things about them. You can start very simple and already achieve like really good results. But you can really, by making smart configurations in these neural networks, you can really push them to all new heights. So one of the problems with this kind of neural network is that, I mean, you can probably imagine that if you have the error right here and like one error value, and this error value then has to adjust all these weights, it's quite noisy. Like you're never really 100% certain that this is adjusted in the right way. So you do it a lot. But the deeper your neural network gets right here, the more uncertain you get. It's something called the vanishing gradient problem. So that means these super deep networks are not possible if you don't do some really cool tricks, like jumping over a bunch of networks and just feeding the information to nodes down the line. And just like it's really fascinating if you read about it, what people are doing with these neural networks to make them work, because a lot of it is really trying what works. A lot of it is really intuitive. So these images, you can see that these layers are getting smaller. So essentially what you're doing is you're condensing information to the things that are most important. Right here, you don't have a lot of space for error, right? So these layers right here, they have to contain the most important information to give you the best outcomes. And I really love that. It's very, very beautiful in its simplicity. And like, if you get into this, have a look how they build ResNets and how they build different configurations of networks and how you can really play around with it. So 2 slides back, sorry for the mix-up. It just felt better to talk about convolutional neural networks first. But yeah, the idea here is basically that artificial intelligence is this idea that we have a computer that is as smart as people. And I think a lot of people are going away from this kind of definition because it's really hard to define how a person is smart. Like, psychologists really have problems defining intelligence in a lot of cases. So defining that a computer is more intelligent than a person gets really hard. So a lot of times artificial intelligence is a computer doing something the computer couldn't do before. Then we have machine learning, which is this thing where you feed it data and you find relationships in the data to classify data, to change it into something else. And deep learning is really, really just neural networks that have a lot of layers, so that get increasingly complex. And there's not a lot behind deep learning. It's a lot of like the math that you need to know for this is matrix multiplications and additions, but additions are easy, and calculus, because you have to calculate the gradient, which, yeah, that's kind of almost it. There's a bit of statistics in there as well, but you can learn that on the fly. Like, you can learn it as you go, and that's kind of how I did it. In geophysics, I didn't really learn about statistics back in the day. So all of my machine learning knowledge is self-taught. And then when I got really interested in it, I did take courses on it at university, and like, I just kept going. So what is the connection to geoscience? And here I'm going into one of the papers I've written during my PhD, which is seismic data again. So here, this is 4D seismic. Essentially, we have one seismic acquisition that was taken back in time and one seismic acquisition over a reservoir that was taken later. So actually over 10 years later. So one of the problems is that our seismic acquisition has totally changed. Like there's a different acquisition system, and of course the geology changed. And we're interested in the geology, not in the acquisition change, right? So we want to match them. And I know that the match basically looks like it didn't change. Like putting these images next to each other is kind of what really happened. I think up here in the fault, you can actually see it. So let me just get the pointer out again. Right here, you can see that there's like a small fault, or maybe an artifact from the illumination. And in the matching, you can see that this is actually like moved up again. Whereas right here, it was connected. So there are like tiny changes. So let's have a look at the difference, because like that's actually showing what happens. On the left right here, this is the unmatched difference. So we can see that there's a lot of variation in here that is just like acquisition noise essentially. And right here in the reservoir, there like something happened, but this is something we call 4D noise. Like usually we want to get rid of this 4D noise and still have the changes that actually happened. So using this method, that is a neural network, like a convolutional neural network, I was able to match these. And the really cool thing is that with neural networks, the training takes time. So you do all of that on GPU hardware. So this thing right here, and you train these models for some time. Like this model right here, I trained for a day. But when you do the prediction, so when I do the matching, it is done in seconds. So it's as fast as the super simple models, but it is much better, much more accurate than the simple models. Usually as good as the as the super expensive methods that sometimes take weeks to calculate, like inversion-based 4D seismic matching. Takes definitely days, sometimes weeks, depending on how much data you're matching. So you have this entire thing that has this really, really great performance, and it's doing all of that quickly, which like I love that part, that you can basically take your calculations and do them before you actually need them, and then just apply them to the data. So it's really front loading a lot of your time. But you may wonder, like, I could just show you something that is like closely matched, right? Like it's easy to just add some amplitudes in here, but that's not how the network works. Like this network basically finds the shift in the data. So it doesn't add any amplitudes in, because that's cheating. That's not physical. That's not what I wanted for this, because you can always just add in amplitudes anywhere and like cheat. That's not how we should do things. But if we shift around, we're preserving the energy of the system. So we're really not inventing anything. We're just doing interpolation of the data that is there. So what we can look at is our warp field. So essentially the shifts in time. And we can see right here that we have a more reddish part here, some blue stripes over here, and again, some reddish part over here. And like, if you squint, I think you can see that this part is also more reddish. Deep blue down here. This part is noise, to be honest. Like this is a mismatch, but we're also not interested in this because this is our reservoir. Yeah, but this is one of the classical dynamic time warping methods that are very fast, but not that reliable. But a good baseline method. So really this network that doesn't know anything about seismic data, which actually was developed on medical data, on brain images, can be applied to seismic data to match seismic data by finding ideal shifts. and that's for me a really cool thing, that you can, like, by thinking about what problem you have in your data, you can figure out a neural network configuration that can solve this problem for you without like cheating by adding amplitudes or stuff like that. Yeah, so I didn't show you the architecture because I wanted to keep it light. Talking about the architecture means I have to talk more about the theory behind neural networks and all that stuff, but paper is freely available. Also, you can write to me, I can send it to you. Like, I'm like, you can probably hear I'm really proud of this work because it's kind of cool. It's finding a different way to use neural networks by using this shift instead of just simple matching. And yeah, this is one application in geoscience, like one very in-depth application, right? I'm sorry if I lost you, but it's going to get easier now, because like, what else? I wrote the paper that Julio mentioned about 70 years of machine learning in geoscience, where I read over 300 papers actually, to write a review of machine learning. And people really try a lot of stuff, and a lot of stuff works, which is amazing. Like, people generate synthetic data using modern deep neural networks, and this is not just in geoscience. Like, okay, I'm European, and there's CERN, the Large Hadron Collider. So the thing where they found the Higgs boson, the thing that, like, the little particle that essentially helps us understand gravity. And they were able to find it there. And part of it is simulating a lot of data. And they use deep neural networks to simulate that data because it's much faster once you figure out your system. Earthquake localization, you can use neural networks to get out some of the uncertainty in the localization and in the amplitude picking of your seismograms. Drill core processing. So that's actually an open source library. So if you're working with rock cores and you have the images of them, there's a neural network library that finds the core in the image and then gives you back basically stitched together core images, which I think is really useful. Like, every time we worked with core in some of the papers, and it's a lot of work. Like, working with actual rocks is really hard. That's why I started geophysics, because you don't actually have to work with rocks. It's much easier. If you just make your rock swing, much easier. So clustering well data. For one of the hackathons, we built an app essentially that, instead of doing cross plots, like the standard cross plots that you know from your well data, we took all the data and clustered all the data. And that in and of itself was okay. We were happy that it did anything, but we had some information about the wells. We knew where oil was. And basically, we could go in and localize missed pay in like open wells. And that's kind of like, by just applying one of the methods that are standard now on all the wells, we were able to find that in a hackathon project, in a weekend project. Like, it's like, I really love machine learning. It's really cool what you can do with it. And like, with all the open source and with all the sharing today, it's so easy to get into. People do prediction of volcanic activity by monitoring the seismic activity. So if you have tremor patterns, for example, you can use deep neural networks to do processing of these. And something that I'm working on right now, at GMV, starting this month, is satellite data. So stuff with Earth observation, open data from Sentinel-2, Sentinel-1 is, yeah, I mean, it's geoscience, it's remote sensing, and like, you can do so much with it, like predict droughts, predict floods, see the impact of these of these events on land usage, like farming, and how settlements develop. Like it's so versatile, right? Because these methods are, like, if you think back to these filters, what they depend on is that you have a local connection between your data. And like, that's true for images, that's true for video. Like for us, that is true for seismic data, that is true for rock imaging. One of the papers I did with a colleague was on uh, uh, backscatter scanning electron microscopy. So little images of chalk. And we were able to basically, instead of him going in with a ruler and measuring every chalk, I was able to take the image and use a machine learning algorithm to find the ideal boundary between the little grains and the background. And then I just calculated the circumference of the grain, and was therefore also the orientation and all that stuff, because once you have the segmentation, you can do all that stuff with a computer. So I was able to do digital granulometry with it. And like, it's so fascinating what you can do with this once you get started, because there's so much behind it. Yeah. So how did I change careers? Well, I'd say participate in hackathons. Your ideas are probably great. You probably have ideas that no one has had before, but you really, you have to try them out. And your ideas only get better if you share them with others, because other people then can build on these ideas. And you can really, like, some of the best ideas I had for my PhD came from going to hackathons and listening to people that are smarter than me talk about machine learning, encourage me, and also just like playing around. Like, I never wrote a paper about this clustering that we did, but it's out there. You can find it on Google. It's on my website, and like, people look at it and they're like, oh my God, why didn't I think about it? And it's really cool. Like, now people can find me in that thing. So it's really nice to have a portfolio, in a sense, that people can find you with. Compete on Kaggle. Kaggle.com is a website where they have machine learning competitions, data science competitions. It's a really good thing. You will probably not win in the beginning. If you do, you're the outlier. Like, all hats off to you, but you will gain experience, and a lot. And also on Kaggle, like Julio mentioned, I was at the Kaggle days. You can get a lot of clout there, because like, you are hanging out with people from Google, from NVIDIA, from H2O AI, from like all these places that have basically hired away a lot of the Kaggle talent, because those people know how to deal with the real data. Like, those are real data problems. And like, I, for myself, I got started easy. I got started with seismic data because TGS put some seismic data on there and wanted it interpreted with a deep neural network. And so I did, and I did okay. But my claim to fame was writing a notebook that a lot of people could then read, and basically the data scientists learned how seismic data works, and the geophysicists learned how machine learning works. So that was kind of a win-win. But after I did that, I basically wrote like almost the same notebook for a medical competition, where there were X-rays of lung images, and they wanted to find like air in these lung images. And it's the same system. You use a certain type of neural network. And yeah, I wrote like, it's not that hard to describe to people how X-rays work, right? You look it up on Wikipedia. I wrote a bit of that for the data scientists. I wrote a bit of machine learning for the medical specialists. And it was really, really, like, people loved that notebook because it kind of put one on one together. And yeah, a lot of people got to know me through that. And it's amazing. Like, when I was at SCG, one of the organizers from TGS actually, like, I didn't know him, but he came forward and he's like, hey, thanks for that notebook. And I'm like, okay, cool. That's awesome. So when you put your stuff out there, when you share stuff, I notice a lot of good comes from it. Like, you shouldn't expect anything. There might, like, nothing might come of it. It's quite possible that nothing comes of it. But if you don't do it, it's certain that nothing will come of it. If you do it, you have a chance that something comes of it. And like, my boss right now basically told me, he hired me because there's like, I have a lot of knowledge in a lot of different places. I've tried out a lot of different things, and I'm an expert in a lot of very specific things. So I'm really good at these 3D neural networks that do computer vision. I'm really good at 2D neural networks that do computer vision, which is amazing for satellite data, which I'm working on now. So I'm an expert in that, but I can make the connection with a lot of different other projects. And this is kind of what a T-shaped person is. You know a lot about a lot of things. You also know that you don't know all these things here. Like, I'm not a medical expert. I don't know the specifics about X-rays. I wouldn't dare to say I do, but I know enough to kind of make the connection. And if I need to know more, I can still talk to the specialists, to the actual medical practitioners, to the radiologists, right? So it's really like, knowing what I know also helped me know what I don't know. And that's a skill in itself. And it's really, so this is the T that I'm talking about. So really try to learn a lot of stuff, be curious, build these projects. And I put get familiar with math on there because, like, you don't have to be a math wizard. I almost failed my studies, my geophysics studies, because of math. But like, in this specifics, like, have a look at 3 blue, 1 brown. If you can't remember, just ask me later. I can show you the videos. Amazing YouTube channel for free, everything for free, that explains the basics of the math that you need for machine learning. And that's all you need. So yeah, start a project today, because application is for engineering, for you geoscientists, is worth much more than theory. And yeah, that's my talk for today, I think. If you would like to go to Slido, my words are failing me, Slido, and share your main takeaway of today, you can share several if you want. That make me very happy, because, like, I want to know what you actually took away from this. But this is my last slide. So if you have questions, I think we have a Q&A as well. I barely made it in time.
Yeah, we actually have a Q&A question. So Jesper, thank you so much for your presentation. It was actually quite interesting to see where we can use deep learning, machine learning, artificial intelligence. And I believe that something quite important during this difficult time is that, as you all know, we are going through an oil and gas downturn. So by listening to Jesper, we can know that there are other ways where a geophysicist can work, where he can develop and try to, to develop your skills on other areas if you cannot find a job in the oil and gas industry. So thank you so much, Jesper. So now we are going through the Q&A questions. So guys, if you have any question, please do not hesitate to ask Jesper. Or to type your question on the comments below.
In case you want to make your questions in Spanish, we can help you with the translation for Jesper, or maybe Jesper can try a little bit of his Spanish.
Es posible que lo entiendo, pero
Jesper, well, I do have a question. Yeah. And how do you feel now that you have changed path, changed your a little bit away from oil industry. How do you feel now?
Excited. So like every time I sat at a table with people from the oil industry now, it was basically talk about lower for longer, right? I don't know if you heard that saying as well, but they were always talking about, okay, the oil price is going to stay low now. And people were like, during my PhD, I worked a lot with the people from Maersk, and people were always afraid of getting fired, like the entire time. And that was in Denmark, where people don't really get fired. Like, it's really hard to fire someone in Denmark, but like there were layoffs the entire time during my PhD, and I have job security now, and it's really nice. Like, I have a salary, and I'm working. So also, the projects that I'm working on right now, there is a project that is working with train data, like actual trains, like the metro. There's projects where I work on identifying cocoa fields in the Dominican Republic. There's actual projects that help people, like the floods and the droughts. We have a project on drought identification. Like, I feel like I'm helping people now, and I'm loving it. Like, it's really good. Like, yeah.
Yeah, it could be possible to use satellite images to find animals, like wildlife animals on those images, and count them. I remember I saw a project on the Scottish Hackathon. They were looking for
the seal one, yes.
Yeah, that was pretty good. My friend,
I love that so much, yeah.
I don't know if Hassan is still here, but one of my friends joined that team. I stayed with the team that was going to do the dynamic time wrap for well correlation. But yeah, the seals one was amazing.
Was that together with Tony Halam?
No, they were working on seismic and identification, like faults and everything. I met Tony that day. Wow, he's really cool too.
Okay, Jesper, there are some questions here from the audience for you. Is there some, Andres Ambros is asking, can you talk a little bit more about the work you're doing with ML?
In what sense?
Could you elaborate a little bit more, Andres? Like what?
Well, there is another one. He says, hi, Gaston Thompson. Hi, Jesper. The webinar was fascinating. Thank you. Could I like to ask you about statistics? Do you think it's important, or do you think math is more important? And the other one was about the YouTube channel. Could you write a name, please?
What? The last thing I didn't understand. Sorry, could you?
Yeah, I think they're asking you about a YouTube channel. If you have one, you can share it.
I have one. Just look for my name. But the YouTube channel for the math is 3 blue, 1 brown. So I don't know. I can't find the chat right now. I'll actually stop sharing my screen for now. So the YouTube for math is 3 blue, 1 brown. And mine is just super small. So if you want to find mine, just Google my name. The part before that. So math was, I think statistics is just math with a little bit different rules. Like and for machine learning, the basics are really important. You have to understand some of the basics. So what is the mean squared error? So how do you calculate these errors? You should really understand that. But a lot of the things you can learn while you're doing it, I think. And with statistics, especially, if you just keep learning, and if you find something that you don't understand, you try to go understand it, that should be enough, in my opinion. So there's, for example, I was training these models and they were doing all right, but then I had a look at the error across my entire data spectrum, and there's something called heteroskedasticity. I can't say it. Heteroskedasticity, something like that. And essentially, what happened is that my model was performing really well on this part of the data, but the errors, like how bad my model was performing, was getting worse over here. And that's a concept in statistics where which is this word that I can't say, but like I looked it up, then I understood it, and then I could work with it further. So really, basics of statistics, really important, but like I don't, like in a lot of statistics, like in a lot of applied machine learning work, you don't really have to understand all the probability theory. You will understand a lot of it through application, I think, if that makes sense. If you want to do research in it, that's an entirely different, like you will not get a research job or a PhD in machine learning without knowing a lot of math and a lot of statistics. But like machine learning engineering, applying machine learning to geoscience problems, you're fine. A lot of it is, you can just do it in Python.
Thank you. Any other question, guys? Jesper, well, while somebody else asks a question, I remember you have a Python course, right? Or data science course?
Yeah.
The platform. Could you share it with the guys, like in case they want to enroll?
Yeah, sure. Let me just get to my browser again. So it is on Skillshare. Skillshare has a lot of courses. I don't know if you watch YouTube, but like people like Mattia Vella and stuff, I think they all have like Skillshare courses. And if you take the link right there that I put in chat, you get, if you sign up within the next 5 days, you get 2 months for free. After that, you have to pay for it. But it should be enough to take my course and a lot of other really interesting courses. Like there's a lot of creativity, painting, and like productivity on there. I don't know if you watch, like one of my favorite YouTubers is Thomas Frank, who talks about like productivity and stuff. And I love his course. It's really good about like building productivity systems. It helped me a lot in my PhD to get like organized. Yeah, but yeah.
All right. Well, the link to the course is there on the chat, guys. I strongly recommend you to go and check Jesper's course. He was a little bit worried about not having enough students at the beginning, but he has had a lot of people. He's really good. There's a question by Victor McDonald. Hi, Jesper. Can you talk more about one of the best projects in machine learning that you have worked in? And what was the main challenge on doing that project?
So the thing is, I kind of really like all the projects I do because I always find something interesting in there. I always try to find something new that I have to learn about, right? Because there's like, so one of the awesome but also terrible things in machine learning is there's always more. You can always read more, learn more, know more. So I always try to be one better than the one before. So, but like one of the super common challenges in machine learning is data cleaning and data validation. Like I said, the math and all that is relatively easy, but in the clustering that I talked about, that I really like that project because it was one of the first ones where I really applied machine learning as well. We were getting really good results and it was really amazing. We were super excited, but on day 2 of the hackathon, we realized that the person that did the data cleaning forgot to take one of the columns out. And one of the columns was essentially a prediction for the labels. So it was really bad because essentially we were telling our algorithms the solution, and that's never a good thing. So really, the biggest challenge is validating your model. So you always have to do more to make sure that your model is actually real and not learning like some like some hidden signals that you forgot in the data. Like on the Kaggle website that I was talking about, there was one satellite challenge where they wanted to where the challenge was to find icebergs or ships. It was actually from Equinor, back then Statoil, and so the challenge between icebergs and ships from satellite data is really hard, but someone solved the problem because the data that they gave us in the competition was satellite data, and actually all icebergs were taken from directly above and all ships were taken from an angle from the satellite data. And someone found that in the data and just build a model on that. So when you build your models, you always have to think about how might the computer be smarter than me? I don't know, like I don't know enough Mexican culture. I'm really sorry about that, but like there's the stories about golems. There's the stories about the monkey paw, where you ask for something and you get exactly what you asked for, but not what you wanted. And I feel like machine learning is exactly that. You will get what you asked for, but it might not be what you want. And you really have to keep looking, how might the machine be fooling me?
Have like cleaning your data. That's like the first thing. The first time I tried to get like real stuff on machine learning, I was doing forecast production for wells, oil wells.
Mm-hmm.
But the first model I ran, I took 7 different fields. They were on different geological features, of course, because they were from different areas. So I was getting garbage because I was not like cleaning the data on the proper way. Then I started to clustering for geological features, blah blah blah. The wells that are running, the wells that are not running anymore, blah blah. And the model got better. I mean, at the end, we stopped working with it, but it's, I mean, as good as a forecast could be, right?
Yeah.
It's like oil well forecasting, that's not that accurate, I think. Well, I haven't seen any model that claims to be the best one. Well, many may claim, but who knows?
It's a lot of magic involved, isn't it?
Exactly. You said golems. Maybe in Mexico we will say cheneques. That is like small goblins, laluches, like goblins. So, some people leave coins or money for goblins to bring more money. So maybe that will be a Mexican way to explain the goblins. All right.
Awesome.
There's another question. It says Arturo Ruiz. Hi Jesper. What do you think is the best approach for a person with a geoscience background to learn machine learning?
Basically, so I think the easiest way is if you have some kind of data, where you have data and something that you want out of it. So like in my example, it's seismic interpretation, right? I have the seismic data and I want it interpreted. So I have some kind of labels. And usually if you already have some kind of data and some kind of labels for the data, it's very easy. And then honestly, something that you're interested in usually helps, because then you start keep doing it, right? If there's no real problem where I can say like, oh yeah, that's something that everyone should start, because like geoscience is so different. Like there's geochemists, there's geologists, geophysicists. So whatever you find interesting and where you have some data that is like a well-contained problem, that's usually the best to start. And then just look on YouTube, and also like the courses on Coursera. You can watch a lot of them for free as well. Look for information there, and there's like the deep learning book, which is for free as well. So a lot of resources where you can look up and learn. And like in my opinion, Python programming is really good. So scikit-learn and Keras are very easy to start with. I'll just type them in chat as well. So scikit-learn has a lot of classic machine learning algorithms in there that you can apply, and it's very easy. If you have a look, you will be surprised how easy it is. And Keras is for neural networks, for deep learning. And once again, like, it's more complicated, but you'll also be surprised how easy it is to get started with them. There's a lot of tutorials. People love sharing this stuff. This is also something I love about machine learning. People share so much. Like, try to find geoscientists who share their code. It's really hard. Like, there is a growing amount, but in machine learning, a lot of people do not accept your paper or do not cite your paper if you don't share your code. If they cannot reproduce what you've done, they don't believe you, because a lot of the times the code tells what shenanigans you've been doing with your data to make it work. And like, if you have an honest paper in machine learning, you can find the code openly available and you are allowed to copy it. Yeah. Go to the software underground. A lot of like geoscientists that are sharing their code are in there. And yeah.
Yeah, that's a good starting point. Sometimes asking questions over there. There's a machine learning channel. So there's people posting things about machine learning, not all the time, but from time to time. It's not like every hour, but maybe every 2-3 days, people is sharing the stuff. That's a good way to start. Coursera has a data science IBM course.
Mm-hmm.
That's another way to start. If you're not interested on getting the paper, you can take it for free, I think, and get the knowledge, but not get the paper. Eventually, if you are like in the need of having the paper for a job or something, well, you can pay for it and you can get it.
Yeah, exactly. And like, what like, you're much better at me sharing links to stuff I've done than me. Like, my introduction would be, hey, I'm a geophysicist, and that would be it. But so I've written this overview paper over the 70 years, and in there I have example code for everything from standard machine learning, like random forest and support vector machines, like where back in the day, you really needed to know your math to be able to use it. And now it's really easy. The code is in the paper. So have a look. It's free in the link. And you can just copy it and use it with your data and like then start learning from that, if that's a starting point you want. But yeah.
Yeah, and you can get the knowledge you get like doing machine learning in the oil industry and take it to another industry. For example, now with the COVID, there's opportunities there. The government, I'm pretty sure Mexico's government, Mexican cities could use some machine learning or some data science for their stuff. There's opportunities there. I mean, we may be geoscience people, but we have abilities, we have knowledge that we can use in another field, and there's no problem about it.
Yeah, so I think one of the things that helped me a lot in being really good at machine learning is that in geoscience, we have so much uncertainty, right? All our data is uncertain, and then we do not actually know what's under there, even if we have a solution. And even if we, like, I worked a lot in oil, sorry for referencing oil all the time, but even if we drill and we hit something and we find something and we produce it for 10 years, 20 years, we don't know what's actually happening. And you're like in this super uncertain space, which helps a lot with machine learning, because like in machine learning, too much certainty is the death of a model. Like good models incorporate uncertainty and work with it, and noise and all that stuff. Like all this stuff you already know, complexity and thinking about systems. Like if you're a geologist, you have to be able to look at an outcrop and really make sense of it in deep time, right? And like thinking about these complex systems is so valuable in machine learning that you actually have a bit of a head start, I think. Like, but maybe that's just like my romantic idea of geoscience.
Geoscience.
Yes,
Yes.
I find very interesting and very inspiring from you that you said at some point in your talk, like it's not important or it's not specific thing that you need to be very good at maths. I think that's very inspiring because sometimes I think, at least in my case, and I guess several of us, think we have to be very good in maths to start programming. And I think that's a very good thing that you mentioned. And also, I would like to ask you, you have several articles written, right? So what do you advise to the audience to do, or how do you advise us, like, to start to write an article, or I don't know, to get the inspiration, or to say, okay, I will do it, I will write an article. What is your point of view about this for all of us? Thank you.
It depends a little bit. Do you mean scientific article or like blog article?
I mean, like, yeah, scientific article.
So let me start with blog because it's easier. So I started my blog in 2011 because I realized scientists have to write a lot, right? You have to be writing articles and like with your colleagues and all that stuff. So I wanted to get better at writing because I knew I wasn't good at writing. And blogs make it easy because there's no one that tells you this isn't good enough. You just put it out and people like it or they don't. And so that's where I got a lot of experience writing and just thinking about things by writing. And like for articles, it's much easier to get like conference and workshop papers, I think. So get started with that. If you have a good idea, try out that idea. And writing, you get better at writing by writing, which is terrible because getting started sucks. It takes so long and like it's so hard. But the more you write, the better you write. And so it's really practice. It's like a muscle. The more you do it, the better you get at it. And that's why, like, if you don't want to have your own website, I understand, like having a server and all that stuff is really annoying. But like, you can write on Medium, you can write on dev.to. So that's medium.com. That's dev.to. Dev.to is more developer focused, but you can write and really refine your thinking as well. I think like people who write have better thoughts because they think more how you can put it in words, right? So if you write more, you will become better at writing. And with scientific articles, it's also really good to have good mentors and good professors. Like getting feedback. Like scientific writing is a bit weird because I don't wanna sound mean, but a lot of papers are written in a way that they're not understandable, right? You try to sound smart because you want to sound smart to the people, and it's a certain way to write. So I actually took a course on writing scientific articles because I try to make stuff understandable, and I like to describe things in words, not in equations, because words come easier to me than equations. But yeah, like especially scientific writing, having collaborators that help is really, really valuable. And yeah, writing, a lot of writing.
Thank you very much. Yeah, I think at the end of the day, that's the main point or the main task of science, right? To make things better. So maybe I think that should be the way, like make things more friendly for people to understand, not just for a specified group of people or something. Thank you, Jesper. Is there anyone having some questions for Jesper in the audience? Or
I have another tip for writing, actually. Sorry about that. Do you know the app Grammarly? So I'm German, so I don't know if any one of you speaks German, but German grammar is really complicated and we love our complicated German. And if we write English, it's usually too complicated and has too many commas. So Grammarly really helps me. Like I'm using it for my PhD thesis at the moment, which still is way too complicated, but like it's the best.
Grammarly helped me a lot during my dissertation.
Grammarly is like a
It's safe.
software. Yeah, sorry, Julio. I just wanted to share. Maybe I don't know if the audience know what is Grammarly, but it's like an application or software that you can install in your computer, and then when you start to write in Word, for example, it helps you to correct something. So, thank you, Jesper.
Sorry about interrupting you, but
No, it's your conference. Okay, no, don't worry.
Okay, I don't know if there is no more questions, guys. Could you please turn on your cameras? Let's take a selfie here with Jasper just to finish this. Hi, Kimi. Well, 1, 2, 3, say whiskey or something.
Come on, guys, don't be shy.
those are some cool backgrounds.
Gaston, you won a prize. That's the coolest background so far.
Oh no.
Thank you.
My camera just turned off. It got too hot.
Whoa.
I'm sorry about that.
Come back, Jesper. There you are.
Okay, guys, here we go. 1, 2, and ouch. Hey, Santiago, is there?
Hey.
Okay, cool.
Awesome.
Thank you, guys. Jesper, one more time, thank you very much for being with us today. Thank you to everyone that joined today's talk. I think it was great. It was nice to see you, to have you here with us on these Chevening Talks. And I hope we come back for a third edition, maybe in a month or 2 or 3 or 4 or some next year. And yeah, this is an effort we are doing to share with the community, the geoscience community, not only in Mexico. We share the link with more people, and I see people that is not from Mexico here, so that's great. And we will try to keep doing this. And thanks to people like Adriana, like Selene, like Lindsay, like Jesper that joined this time, we will try to keep doing it. Kimi, if you have some words to.
Hi, vielen Dank, Jesper. So thank you so much, Julio, Tanya, and Memo again for organizing this second Chevening Talk session. It was good. I really enjoy, and yes, and if, as Jasper said in the last, I think in the last slide, was about what could you keep in your mind about after these all sessions. In my case, that, as I pointed out in the first Tuesday, not a geoscientist, not a petrophysicist, not anything related. I study international relations, but still not afraid to try something else. I enjoy the talks. I learned a little bit about. Sometimes I thought that you were talking to me in, I don't know, in another language, but still I was able to enjoy, and hope of you enjoy as well. We hope to have new sessions, as Julio said, probably in a month, 2, 3, 4, until next year. But if you have as well any suggestions for our organizing on which topics you would like to cover next time, more than welcome. And from the British Embassy and from the Chevening program, we will keep encouraging this kind of exchanges and spaces of ideas. So thank you so much.
Thank you, Kimi. And
Thank you,
yes,
Kimi.
as Kimi said, if you guys have any suggestions on topics, mostly we are trying to cover geology, geophysics, and a mix of geoscience with coding. I think it's kind of relevant for everyone, especially students. If somebody wants to join and participate, I mean, like giving a talk or everything, just get in touch with us and we can arrange it. All right. So, well, Guillermo, Tania, if you have any final.
Yeah, thank you everyone for joining us. Gracias por unírsenos hoy y a las anteriores pláticas. Si alguien más quiere participar en futuras ediciones, no duden en contactarnos, como dice Julio. If anyone is thinking or would like to participate in these talks, don't hesitate in contact any one of us. Or also, if any one of you have questions or comments about Chevening scholarships, now it's the time to do it. So don't be shy.
Sí, muchas gracias a todos, la verdad, por haber participado en esta segunda edición. Creo que, bueno, esperamos tener una tercera edición. Creo que sería interesante a lo mejor que los que han participado abrir un tipo de encuesta. A lo mejor les vamos a estar enviando una encuesta o algo así para que propongan temas o algo de interés para ustedes y, bueno, recopilar toda esa información y ver qué podemos sacar para la tercera edición, ¿no? Porque, bueno, cada vez creo que las pláticas están saliendo muy buenas, muy interesantes. La verdad la de hoy me gustó bastante y, bueno, muchas gracias a todos, la verdad.
Okay, guys, also that's gonna be it. Again, Jesper, thank you, good night. I think this, are you in Edinburgh right now? No.
Yeah. So it's dark.
I know. Grasshopper Market, Mexican place, a burrito, and a Corona.
Yeah, soon.
That's the best suggestion I can give you.
Today it became illegal to visit other people's homes, so it's gonna be a while.
Ouch.
Well, thank you for having me. It was really, really a pleasure, and thank you for like participating in my silly like polls and stuff. It was really fun seeing you and like being here. And thanks for all the questions as well. I know it's hard to ask questions sometimes, and yeah, I appreciate it. I really do. So thanks for having me.
Okay.
And yeah, have a good day. Like for you, it's day. For me, it's night.
2:30 p.m. It's okay. Okay, guys. So thank you and see you around. Bye to everyone. Stay safe, please. Stay home in the case of people in Europe.
Yeah.
Okay. Bye-bye.
Bye.
Gracias.
Nos vemos, Kimi. Kimi.
Nos vemos.
Kimi.
Don Julio, espérate, no te vayas.